Hi, my name is Patrick North, and I'm going to talk today about EOIR. That's the Electro-Optical Infrared Toolkit that's available for STK. And I'm going to focus specifically on three hard targets that, normally you have different types of applications, and we're going to look at hard targets that are in space, that are on the ground, and halfway between in the air. So we're going to talk today about electro-optical infrared. That's from 0.28 to 28 microns. And essentially, we've got a toolkit that lets you do all of the radiometric analysis, all the physics that happens in that bandpass. And you can put those sensors on aircraft, on satellites, on ground stations, and they can be looking at other objects. So it doesn't matter what your platform is or where your target is, this is going to handle all the physics in that realm. The heritage of EOIR is it actually came from the Space Dynamics Lab. This was originally a tool that the SDL used for missile defense applications. And what we did is we actually took that toolkit and brought it over to STK so that you could use all of the nice STK setup features and then do that radiometric analysis. And we expanded it to say, this doesn't need to be just for missile defense applications. This is a generic physics engine. And that's exactly what we've done. So again, that 0.28, the hairy edge of UV blue, all the way to 28 microns, the long wave thermal infrared. And what we did is we said, well, you've got all the right STK stuff to set up where your aircraft are flying, where your satellites are orbiting, where your ground stations are located, but we need a little bit more than that to start doing the actual analysis. So with EOIR, you get an entire planet out of the box. So you have the global material map. You also have a diurnal thermal model, so things heat up and cool down with latitude and longitude according to the time of day and the time of season. You also get a whole bunch of sample 3D models so that you can start doing your analysis right away. You don't need to wait. You've got everything you need right there when you first install it. And then the outputs, you have visual imagery that you can produce. You can create a bunch of frames and put together a video. You can also report on quantitative metrics. So if you have sensor to target metrics that you're particularly interested in, if you're validating requirements, things like that, you can just generate those reports. So the first problem that we wanted to take a look at was small satellites. So essentially, if we are looking at targets, let's just start with outer space. And we chose this for a reason. Our Commercial Space Operations Center was based on, if we could collect a lot of commercially available SSA data, wouldn't that be great? What if we could do it at a really low cost? And one of the problems is we used a lot of optical sensors for this. And optical sensors, they don't work great when your sensor's in daylight or your targets are in shadow. So right off the bat, with a lot of the lower satellites, we were looking at only 50% operational capability. And I had the great idea. I said, well, wait a second, guys. What if we added some thermal sensors to the mix so that we could see once these targets went into shadow? And I'll go into a little bit of that, but essentially we're looking at space objects as they're orbiting the planet, and specifically we're looking at these small satellites that might be in low Earth orbit. So these are CubeSats, things like that. And I wanted to ask specifically, can we detect these things thermally? So the first question I had is, well, how hot and cold do things get in outer space? There is a Space Environment and Effects toolkit that's available in STK, and with that you have a passive thermal model for your space objects. So that was just one easy way to generate temperatures. You can also Google it, but the results are about the same. We saw that with a lot of I created a generic small satellite, put it in a circular LEO orbit, and we saw that the temperatures varied from about 200 degrees up to about 310 degrees Kelvin. So things get pretty darn hot when they're baking in the sun, as we can see in this plot pattern, and they also get very cold. They drop very quickly to about, we saw with different models, they were going all the way down to about 180 degrees Kelvin. So, and that drop is precipitous. It just almost instantly starts cooling down to that cold temperature. So right off the bat, my great idea to detect these things when they went into shadow didn't look so great anymore. I started getting a little nervous, but I said, well, let's do the actual analysis. So I put together a generic set of 4 optics for our sensor platform. I said, well, let's just give it a decent telescope and let's take some pictures. And right off the bat, on the left-hand side, you have a visible image, and on the right-hand side, you have a long-wave thermal infrared image. And anytime you're looking at a new type of tool, you want to evaluate things qualitatively and quantitatively. And this is a nice example of that. Within a few seconds, we can set up a temperature for our target, we can set up the properties for that, we can set up our sensor, and we can start taking pictures. And what you can see, if you have good eyes, if you're an image analyst, or if you're just a casual image editor, you'll see that the image on the left is sharper than the image on the right. It's a little bit blurrier. And what's causing that? Well, as I mentioned, these are the same 4 optics, so it's the same telescope on both of these systems. They're the same size detectors on the back end. The difference is the visible light is about half a micron long wavelength. The long wave thermal infrared is about 10 microns. So that's a 20 times longer wavelength that you're trying to stuff into the same pixel-sized box. So of course you've got more diffraction, you've got more optical blur in the long wave thermal infrared image. So right off the bat, if we're just taking a look at this software for the first time, you're seeing this phenomenology is accurately represented. So I'm now starting to see the physics as I would expect in real life. So I'm saying, okay, well, maybe I can trust this a little bit better. But, now we're starting to say, well, what about that detection capacity? What are we going to be able to do, detection-wise? So I see the physics, it's generally represented. Let's do some actual analysis. So here we have the hot target on top and the cold target on the bottom. In the visible imagery, it looks about the same, right? So in the visible, we're looking at reflected photons. However, on the right-hand side, the thermal image, we see the hot target is glowing more than the cold target. And we can see the range here is about 120 kilometers. So this isn't too bad. This is, pretty far away. This is good, but this is an easy detection. This is no problem. So I said, all right, great. So the hottest and the coldest targets for this envelope function of temperatures that I'm going to see, both of these can be detected, no problem at 120 kilometers. The problem is in space, we've got drastically varying geometries. So what if we back these a little bit farther away from each other? What does that start to look like? And of course, my analysis quickly fell apart when just going to about 144 kilometers, we now can barely see that cold target. It's only got an SNR of about 10, and that's about where I'd say, all right, it's maybe detectable, but much more distance than this. We just can't do anything with this data, unfortunately. So, my idea for detecting things thermally, when things just get too cold in outer space. But what I was able to do is I was able to learn the phenomenology with this modeling and simulation. I didn't need to collect a lot of field data. I didn't need to do operational collects. I could verify this with this simulated data. And also, this gave us a really easy way to say, by the way, again, if I'm looking at this tool for the first time, could I validate this? And actually, it's a really easy piece of validation because you can, with EOIR, you can click on the targets and say, all right, well, what's the in-band radiance? How much energy is being output by this hot target and this cold target? And then you can go to a third-party tool. I use Spectral Calc, and that's a great, easy place to just plug in the black body characteristics and then calculate what the thermal emission should be for this target. And we can see right off the bat that the ratio of the hot to cold target matches spot on. It's really, really good. And we can see the absolute values for those thermal emissions are right on as well. So that's fantastic. So, within a few minutes, we can see that, qualitatively, I'm seeing the types of things I would expect, and quantitatively, I'm seeing the types of things I can expect. So that's great. So that was an easy first problem to look at. It's just how hard would it be to detect these objects in space thermally? Some next steps, there's a lot of other things that you could do to extend this problem. But in general, I just wanted to cover, just that one specific venue. Now, what could we do next? Well, a hot topic recently has been looking at wildfires on the ground. So I said, well, that's great. So I've got my space target. Now let's look at a ground target. And for this, I'm not an astrodynamics guy. I'm a sensor guy. And what I wanted to do is say, well, let me do my sensor dynamics just flying a generic circular low Earth orbit over this particular area that I happen to know well, Exton, Pennsylvania. That's where our headquarters is. So I picked that and I said, well, what could I do to simulate wildfires on the ground here? These are hot spots. So the inputs, rather than the previous example where I used a SEAT, Space Environment Effects tool, to generate the temperature data, and I used generic target models for my satellites, I said, well, for this one, I'm going to use a reflectance map, a high-resolution ground reflectance map. And in addition to that, I'm going to generate that hotspot map, that temperature map, custom designed. And with EOIR, you can take those custom products. So again, if you have additional data that's relevant for your particular problem space, you can load in your own custom data. And I said, well, now that I've got these, this high-resolution reflectance map, and I've got this high-resolution temperature map, what would this look like? And during the daytime, I took the same satellite that we built in the previous example with a visible sensor and a thermal sensor. And I said, well, let's take some pictures. And right off the bat with the visible sensor, we've got a nice overview of what the imagery looks like. We can see the custom reflectance map, but I don't see any hot spots here. However, if we were to load this up with a long-wave thermal infrared sensor, those hot spots, they show up right away. So it's a real easy way to detect them. And that's exactly why thermal sensors are perfect for this type of job, because that's what they do. The emission from these, again, these aren't blazing infernos that are glowing hot in the visible, but they're hot enough where these hot spots are going to show up in a thermal sensor, no problem. If we were to take this same image at night in the next example, so here, again, same setup at night. As I mentioned, EOIR is a physics engine. So now that there's no reflected illumination, well, in the visible, we might actually start to see some of these hot spots glowing. Again, this is nighttime, and these hot spots, they're glowing just enough where a thermal detector would see them without any of that sunlight being reflected off the background. But of course, the thermal sensor at night is fantastic as well. That's going to do really good detection, and you'll also have more context for your data. So this is a piece of cake for detection. However, what if we were going to put this in a mission context? So rather than just detection, we can see how well a thermal sensor does, but what resolution might we need for the job? So instead of saying, how well can we detect it, what if I'm trying to provide data to a fire chief who's going to be deploying assets into the field, and he needs to plan ingress and egress routes for his firefighters to be able to safely get into a neighborhood, do some, do their job, and then get out safely. And one of the problems with a lot of sensor design, again, I'm a sensor person, so I've seen this happen too many times. You'll have the end user who knows their problem really, really well, and you'll have a sensor designer that'll give them a spreadsheet like this and say, well, okay, you said you needed resolution to be able to see what's going on in the neighborhood. Well, here's your geometric resolution. By the way, that blue number, which is really good resolution, we can't give that to you for nothing because you're going to have optical blur, and see this system Q, that's your blur in pixels, that's going to become a red number. And if I'm a decision maker who knows my mission space really well but doesn't understand these system parameters, I'm left out of the conversation at this point. I no longer can provide input because I don't understand what these mean. This is essentially a system trade study where if you're locked into certain system design parameters, like you're only going to have a certain size aperture that most systems would be able to operate at, and you're only going to have some number of detectors and detector sizes that you're going to be able to commercially acquire or generate, manufacture. So you're left with a few of these trades like, well, maybe we can, we know we can only downlink so much data, maybe we can get slightly bigger detectors, maybe we can get a slightly longer focal length. What is the sweet spot for this? And EOIR lets you do an actual image trade study. So here we have a grid. Those are the same system parameters that we saw earlier. This is the focal length. You can have a 1, 2, or 4 meter focal length. You can have detectors that are 40, 80, or 160 microns. Here's what that looks like in context. So now all of a sudden a decision maker who needs to route his firefighters through this dangerous neighborhood, all these can do detection. Every single one of these is fantastic at detecting these hot spots. However, which resolution do you need to navigate through this neighborhood? This is the mission context that only the end users are really going to be able to know. And now they can say, wait a second, so this diagonal that goes right through the middle, I can see the context, I can see enough area where I could say, all right, now I've got enough perspective to safely route into and out of a neighborhood. This top right corner, that's actually zoomed in too much. I need more context than that. All the way at the bottom left, that's too zoomed out. I can't even see what's a street versus what's a pathway versus what's a fallen tree. So all of a sudden, maybe now this diagonal makes sense, but each of these different combinations of system parameters are going to cost drastically different amounts of money to build and operate. So now we can say, well, if I can do my job with any of those along the main diagonal, now all of a sudden I can start playing those cost games, and I can be smart because I can say, I know I can do my job with this, this, or this. If this costs me $1 million, $2 million, or $4 million, all of a sudden I've got an easy way to provide my mission context to the budgeting and acquisition process. So that's fantastic. Now every decision maker can take their unique perspective, know what is important for their problem space, and can then apply it into a design requirements or acquisition process. And this is just a flight, if we were to fly through the scene, what would this look like continuously if we were recording this with a long-wave thermal infrared sensor? So again, you can provide those imagery for trade studies, for detection analysis, or if you just want to create a video to contextualize the problem for somebody who's maybe thinking about acquiring a system like this or operating in a unique new way. So that's our wildfire scenario. Now, the last scenario that I'm going to talk about is one that's been very important lately. So we've looked at things in outer space, we've looked at things on the ground, and now we're going to look at a hypersonic glider flying through a scene. This is again, I'm a sensor guy, so what I did is I asked our aviation folks to say, is there a hypersonic scenario that we already have built that I could just add my sensors to? Again, I didn't need to do any setup for this. I took a pre-built aircraft scenario and I said, all right, you give me something that you have built, that you're the experts, you know this problem space, and then I'll add sensors onto platforms and do some analysis. And this is an example of an aircraft that's flying at hypersonic speed. So this is going right about Mach 6, and it's flying at a constant angle of attack, which means it's going to be pointed at a certain angle, and it's actually going to, you'll see the altitude jump up and go back down. That's called a phugoid motion, which I've only been told is that's how it's pronounced, and apparently this is going to be bouncing up and down throughout its flight path. But it's got all the right aircraft, aviation. It's got all the right dynamics for that aircraft. And now I can say, all right, now being a sensor person, now I can say, this is what the problem space looks like. Now let's start learning some phenomenology about that problem space. So on the next slide, I said, so when can I detect this hypersonic? That's a big question that a lot of folks have been asking lately, is how detectable are these objects? So again, with the previous examples I showed, we started with basic models and custom inputs. For this one, the inputs for me was, I need to know what these temperatures look like for these hypersonic aircraft. And what you can see from this top right plot, that's a graph of, based on how fast something's flying and what altitude it's flying at, each of those contours are envelopes for what the temperature would look like. So if we're flying at about 80,000 feet at about Mach 6, our temperature is going to be about 1,600 degrees Celsius. That's amazingly hot. The problem is not the entire body of the aircraft is going to be that hot. If you look at the sample 3D model of a hypersonic primitive, we're going to have the leading edge is going to be 1,600. The problem is the top surface, based on the way the airframe works and the fluid dynamics of this, the top surface of that is going to be almost ambient air temperature. It's directing all the airflow underneath that aircraft, and the top surface is unfortunately the very coolest part of the aircraft, which is what most of our overhead thermal imaging assets are meant to detect. So this is a really tough problem right off the bat. But now we've at least got the input, so we can start playing these phenomenology games. So what I did is I said, I've got this scenario where this hypersonic is flying with that phugoid motion and it's traveling along the west coast of the United States from south to north. And what I did is I added a low Earth orbit elliptical sun-synchronous satellite, and I said, I'm going to use the Orbit Wizard and SDK. I'm going to add a generic satellite. I'm going to have it fly around. I'm just going to point a sensor at this target. I'm going to try and take some pictures. Now, from my perspective, I'm very sensor-oriented, and as most image scientists are, we only consider our own perspective, and everything else, somebody else is going to handle that for us, and we don't need to worry about it. The problem is, when you start thinking that way, you completely lose perspective of how much goes into so many different things. For example, when I was in Florida and I was talking to some test range folks at Kennedy Space Center, I got a chance to look at a GOES-R launch. And I remember when I went up to the rockets with my kids, and we're a family and we're going around the tour, and I looked at the rocket and I just kept looking up and up and up. And I finally got a little sense of how hard it is to get some of our satellites into outer space. That same thing with this scenario. When I created this and I added my generic satellite, and I'm just trying to see what the local geometries are, when I started playing this scenario out, and I saw how fast this aircraft was moving relative to my satellite, that all of a sudden was one of those moments where I said, wow, I have never seen an aircraft outrace a spacecraft. We've got a 90-minute orbit on this low Earth orbit satellite, and this hypersonic is moving, Mach 6, I now have a new respect for it, because this hypersonic was flying so fast, I realized if our asset wasn't in the right point at the right time, we would have completely missed this. It would have been gone. That's why, these timelines are so critical, and the positions are so critical for this type of target, these hypersonics, because they travel so incredibly fast, and you can see it in this scenario as we're playing it out, that you need to be in the right point at the right time to even have a ghost of a chance of doing this detection. And we were able to take a look at this and say, all right, now we've got our platform that we're going to put a sensor on. We've got our target motion flying through here. Now, what does that look like from an end user's perspective? And what we did is we created a video of that. So this is a video where This beautiful looking golden satellite flying through the scenario, that's my generic Orbit Wizard satellite. We just had some system engineers make it look really nice. And as it's flying along, again, that's that sun-synchronous LEO orbit. Now I show a broad area thermal infrared image, and that's going to show up in the top left of your window here. We see that little hot spot, that's our aircraft, that's our hypersonic glider. In the bottom right-hand side, that's the local geometry of this hypersonic glider. And that's important because what we can see here is because we're flying in this highly elliptical low Earth orbit, we have a grazing angle where we have a perfect view of the underneath of this aircraft, those hot surfaces underneath this hypersonic. But as we fly along and we get more overhead, you see it just disappears. It disappears into the background because we're only seeing the cool surface of this particular aircraft. And all of a sudden we can now see this is no longer a radiometry problem. I'm learning the phenomenology of this, and all of a sudden it's more of a geometry problem. I realize the critical points to doing these detections isn't necessarily getting the best access times, it's getting the best access angles. So now I've got an understanding for the problem space, again, all in modeling and simulation. I haven't had to do a field test, but I've learned a lot about the problem space, and I can start to do parametric studies of, all right, from these different potential conditions, what could things look like? And if you plot it out, you can actually see there is a plot in blue of the target radiance of this hypersonic. Again, you see those bumps in the curve. That target radiance bounces up and down. That's that phugoid motion. That's essentially each skip, you see a slightly different geometry of that aircraft. And that's why it has that pattern. All of a sudden, I understand the phenomenology of that. That orange line, that's the background radiance. Again, initially, it's a space background because we've got that grazing angle. Eventually, we go over the Earth, we see that shoot up, and we see that crossover point. We know, okay, now I've got my, my target to background contrast is good up until that point in the scenario. That's, that's the geometries I need to focus on. Also, if you can look closely at that orange line, you'll see little bumps and dips. This is the northern latitude, end of the summer. It is a hot land mass with a colder water background. So every time our background goes from land to water, we'll see a bump in the curve. And that's great. Now we're starting to really understand the phenomenology. And this green line, that's if we were to use an effective temperature for this target, it would have a constant radiance. And what we can see is that's absolute garbage. We can't take a lot of these, advanced thermodynamics and throw it out the window and use effective values because we see it's not correct. It's not even close. It's not even close to good enough. So this is a nice way to package the problem and say, again, with SDK, it's easy to add aircraft, add satellites. You don't need to be an expert in any of those areas. You don't need to be an expert in imaging science either to do some of this phenomenology analysis too. I'm just putting together scenarios that are interesting. I'm learning the phenomenology space, and now I can start to play cat and mouse games with this and say, now what if it was taking a different flight path? What if my sensors were in different positions? How well would a sensor on the ground see a hypersonic that was coming in at it? In fact, that's the next question that we asked. In this scenario, this is, again, another hypersonic aircraft, but instead of flying that constant angle of attack and having that phugoid motion, this is a much more ballistic trajectory. So here, this hypersonic goes real high up, and then it starts flying down really quickly towards this ground target. Now, the ground target, which it happens to be a ship, and what we said is, well, this is a great, this is a different perspective, a different flight pattern. What would this look like if our ship had a broad area thermal infrared sensor? And that's what you see on the right-hand side. So you see this ship launches 2 intercepts at this hypersonic that's flying along at it. And the question is, what would this look like on the right-hand side, on this thermal infrared view from this ship's perspective? And what you can see here, that big blob right there, that's the sun. The dot above that, that's actually Mercury. So you see these things in the thermal infrared. This is good phenomenology, but what we can see if we play that again is you can see the hypersonic fades in a little more slowly, then you see it bounce up, that's the same flight pattern that we saw, and then you see the intercepts flying out towards it. And this is a unique perspective where we can now start to do trade studies, not just from space, but simultaneously from the ground, and we can even try different band passes and different atmospheric combinations to see when this might be detectable, how soon is it detectable, what types of things might impact these detections. So now you've seen how EOIR can help you in all these different domains, from air to space to ground, And you don't need to be that image scientist, that imaging expert to do this analysis. You've got this SDK framework, and this is just one of the tools that fits into it to let you do analysis along this avenue for mission analysis, for test data generation, for just playing what-if scenarios and building your own algorithms. Now you've got all the tools you need right at your fingertips, right out of the box. That's my presentation for today. I hope that it was interesting, and if you want, you can check out more about EOIR at agi.com/EOIR. Thank you.